So yesterday we talked about, last week we talked about the compressive flow. So this time we will talk about another type of flow that we can again often assume it that is compressible, but is incompressible again, but we will have to deal with one more phase. So in our previous lecture, yes, connected phase. The video is not yet open. Okay, so in the previous lecture, we talk about the UP formulations. Okay, basically for incompressible flow, if you remember, the formula is very simple. The divergence of the total stress plus the body force. This is actually the balance of linear momentum, and then plus these equations. Let me turn off the light.
It's on.
Yeah, I just want to see whether you can do it. I think that's better now. Okay, let me continue. Okay. So this is the first equation is the balance of linear momentum. The second equation is the balance of mass, and this is for incompressible flow. Okay. So for compressible flow, eventually what we will get is the following. The first thing we need to look at is the balance of linear momentums. In the compressible flow, what we have is that we are assuming that the total stress is equal to the effective stress minus Pi. Okay, and these stress are all second order tensor. Okay, so far so good. That's for the case where the Beal's coefficient is approximately 1. Now then, we're actually generalizing it into compressible solid phase. If the solid phase is compressible, then what we will have is that the total stress is equal to the effective stress minus Bpi. And again, B is actually equal to 1 minus K divided by Ks, where K is actually the Buck modulus of the skeleton, solid skeleton. And Ks is the Buck modulus of the solid constituent, or we can call phase. Okay, as you can see, if Ks going to infinite, approaching infinite, then B approaching 1. Okay, so in solid mechanics, we're simply assuming that K is actually the Buck modulus of the solid skeleton is much lower than the Buck modulus of the fillet, and then the solid one is actually much higher than the solid, and so K, we basically assume B equals to 1. If B equals to 1, then what we would call it the Tasaki's effective stress theory, or Tasaki's effective stress. If B is not equal to 1, that is generalized into Beal's stress, Beal's effective stress. Okay, so there are other implications for the balance of mass as well. So for the balance of mass, if the material is incompressible, then what we have is that we would actually arise a new term, which is actually B times the divergence of V plus the porosity divided by Kf P dot plus the divergence of V equals 0. Okay, so this B term is actually the same as the Bill's coefficients. It's the same one. And this is actually the new one that take account of the fact that the fluid can be compressible. Then again, in the case of incompressible phase, this becomes 0 because Kf go to infinite. Okay, so we end up just deal with two terms. Now this is actually for compressible flow. So for water, you may not consider it as compressible unless for some extreme case. I mean, there are always extreme case. You need to consider extreme high temperature, extreme high pressure, then the general assumption of incompressibility may not hold, or you simply deal with gas, okay, or something that are actually lighter, then you cannot assuming that the stress is the material is incompressible. The phase diagram look like this. So this is an effective medium. Okay, so, and you can imagine that there are some solid there and some liquid inside. Okay, imagine there's a central field and then I'm able to separate it into two phases. The heavy one go into the bottom and then the light one go to the top. You will find that there are two phases. One is W, another one is S. W stands for fluid or the water. S is actually denoting the solid phase, okay? Now this is actually a relatively easy system because you consider the interaction from between the water to the solid and solid to the water. Now, in general, when we consider a porous media, let's look at the circle, and let's imagine there's a handful of sand. So you have that material, sand that are here in small scale. And then you may not only have water, you can have air bubble, or you simply have a little bit of air. A little bit of water. Now the water and then what we need to consider is a three-phase system. Okay, why is the three-phase system more complicated? And that is actually due to the fact that we have to consider the interaction between the solid and the water and the gas to the solid. All the different combinations need to be considered. And they act in a very different way. It's governed by their relative specific surface energy to each other. Now let's consider the case where we have very low permeability. Very low amount of saturations. Let's say 10% of the volume of the void space is actually occupied by 10 to 15% of the void space is actually occupied by water. In this case, then if you look at the representative volume, we will see particle. And we see a lot of empty space. Does that make sense? Okay, in between that empty space, there are actually water. Okay, so how will water look like in this case? So there is only 10%. Are they going to randomly distribute in the void space? Not really. So what happens is that the water is going to form a thin film because of the surface energy. The solid itself depends on what kind of solid and what type of fluid we have something called wettability. As the name implies, wettability governs how easy the water actually get wet. When we say get wet, is that the water droplet is remain on the surface. Your iPhone is specifically treated so that it actually have very high water contact angle so that the water won't penetrate into the phone. Okay, so it's very special. You don't want the water get inside the phone. You don't want the surface to be porous, and you actually want it to be repelled to water, right? Okay, so this is specific treatment. For soil, it doesn't have specific treatment, but naturally it has something called a contact angle. If you look at one small surface, okay, the contact actually look like the contact look like this, and there's something called contact angle. So water, oil, beer, all the different water have its own specific contact angle to a particular type of surface. Okay, so in general, for most of the soil, granite, quartz, that doesn't actually absorb water, the contact angle in these particular regions will obviously be less than 45 degrees, and it would actually form something called a liquid bridge, which means that the water would actually act like this. Okay, so they will form a little bit of a bridge. If you look at this, it's like if you look at it in small scale on one surface, the two water would actually look like this. Okay, so this is actually called liquid bridge, and this is actually affected by also the air pressure. So there's the air pressure that are pushing the material. The higher, the more air pressure, the more the curvature you have for individual liquid bridge. Okay. Now there's also something that are very special about the liquid bridge is that it forms a temporary link between the two solids. Okay. So what actually happens is the following. When the material is actually completely dry, okay, imagine that you have a dry sand. Can you make a sculpture or human face or castle out of it? You basically cannot, okay? So basically, why is that? Because the granular material have no tensile strength, okay? It cannot hold its shape unless it's under compactions, okay? It can actually cause energy to deform it, to shear it, if it's under compactions, okay? But in tensions, it doesn't make sense for the sand assemble to be in tensions. Okay, individual grain can be in tension if you grab it and extend it, okay, but not the entire assemble. Okay, the assemble doesn't really have any tensile strength. Now with the water, then what happens is that now you can build a castle, okay, or you can build human face octopus in those sand castle competitions. So what does it tell? Yeah, the water is sticky, and in the mechanical language, what it means is that it has shear strength, okay? Enough shear strength to support the dead weight of the material. The sand itself has weight, right? Okay, if I can actually use the water to support it. So now the water, what actually means is that the water would affect the material behavior. And in this particular case, where the water from the patch, we call it capillary regions. Okay, basically meaning that it formed the liquid bridge. Now, if we actually go further by increasing the degree of saturations, which is actually the volume of the water divided by the volume of the voids, what we would have is that we will reach another regions where the solid would actually form patch. Now that may look like this. That actually not only connect two particles, but multiple particles, not necessarily 3, maybe 4, 10. If you keep increasing the density, if you keep increasing the degree of saturation, eventually what you would get is the following. You will get something very close to a fully saturated water, but with some air bubble. Okay, does that make sense? Okay, just that cartoon. Okay, now this is actually very interesting. In this this is nearly saturated, so smaller than 100. Okay, but typically, for example, greater than 85. Okay, in between that, here the material actually have an increased shear with shear strength. At this point, the shear strength reduced. At this point, adding the water doesn't increase your shear strength at all, right? Okay, although the air bubble can still transport, and they can also coalescence, and they can actually, it also take energy for two coalescent bubbles to actually merge together. Okay, if you actually, when you're a kid, you probably try to form air bubble, okay? So you can see that sometimes the air bubble collapse together, but they did not immediately form a bigger air bubble. You can still have a membrane. Okay, so any type of these interactions will cause energy, but what we actually are interested is the following. If you're in this phase, the air and the solid, air and the water are basically transport together and interact to each other. In this stage, you have to consider that the air may be very easy to travel, but not so much for the water. Okay, you see what I mean? Because of the surface energy. Because in particular, if the solid phase is actually very readable, okay, or have very high readability. Okay, now this is actually the case when we consider the three-phase material. Okay, imagine that as a thought experiment, we have a central field. If you saturate the three-phase, now I have the air, I have the water, and I have the solid. This is actually kind of like the undergraduate soil mechanics, if you remember. Okay, now the goal of the poromechanics problem is to actually able to simulate the three-phase flows. Okay. Now, notice that in reality, you have more than three phase also commonly encountered case. For example, you can have ice that would actually make it four phase, okay? And you can also, if you work for oil company, you have to deal with the oil, which also have different wettability than solid. And you can also have any other chemical potentials or actually fluid that may or may not be able to mix together, okay? And you have to consider that possibility, how to model the transport problem, okay? So here, we will not consider anything that with a very high Reynolds number, but just more like a sea gauge flow for both phase. Okay, so now imagine that the total volume fraction is 1. Then the volume fractions of the air, and the water, we would actually just partitioning it with a phi label. So we'll call it alpha is now potentially equals to A, W, or S, just phi choice. And the total volume fractions of the phi case is actually equal to 1 always. Okay, does that make sense? Okay, or if you can think about it in the waveform, the rate of change of the volume fraction of the solid are equals to the equal and in the opposite magnitude than the sum of the change of the other two. So, okay, does that make sense? So the proportions could change, but you could not create or reduce any mass, okay? Now here, a lot of time for convenience purpose, we will sum these two terms together, and then we will call it, like what we did before, we will call it porosity. So the porosity, sometimes we will write something like this. V stand for the void space, and then we will have this equal to the sum of the volume fractions of the air and the volume fractions of the water. Okay, or of course that also equals to 1 minus the volume fraction of solid. Okay, so far so good. I just need to introduce some terminology that commonly for the hydrologists or oil company people to use so that we can communicate. Okay, so far so good on the volume fractions. Okay, it's pretty intuitive. Now, we also want to focus on this void space. Okay, because there is an important concept of saturations. Okay, so saturation meaning that inside the void space, how much that liquid that fluid fractions fluid is occupies only the void space. So there's something called the void fractions. Okay, which is actually a different concept. It's actually just the fractions of the area of the phase divided by the void fractions. Does that make sense? So this tells you the fact how saturated the material is. And then we can write it both in terms of the water and the air. Okay, and the one corresponding to the, sorry, this has to be W. The one corresponding to the water is called degree of saturation, the same terminology you will find from undergraduate soil mechanics course. This is the degree of saturation, also denoted as SR. Okay, so let's look at that phase diagram. Okay, now if the degree of saturation equal to 1, what that implies is that the volume fractions of the water is equal to the volume fractions of the voids. Okay, does that make sense? So in other words, that means there is no air bubble in the void space. Does that make sense? Okay, there's no volume, so that means it doesn't exist, okay, in the void space. Okay. On the other hand, if the degree of saturation is equal to 0, that implies the volume fractions, the void fractions of the air is actually equal to 1, and that implies that the material at the void space have no water there. That means it's completely dry, right? Okay? Does that make sense? Okay. Doesn't mean that dry doesn't mean there's no fluid there, just air. Okay. Okay, now this one also have an important relationship is that if you look at it, so if I add the two things together, the void fractions of air plus the void fractions of the W is actually equal to 1. Okay? So what is the void fraction of solid? That doesn't exist because it's a contradict concept, right? Okay, so either the solid, either we are assuming that there's one solid phase, and then then the material is either occupied by solid or empty. Okay, and for the empty space, it can occupy by the water and also the air. Okay. Okay, now I introduce all those terms. It's just not for understanding. This is a numerical course. We need to convert it into numerics. So what we actually need to do is to modify. Is actually to do two things. Okay, one is to introduce the right balance law for us to make the simulation happening. Another one is to introduce the necessary material law to actually complete the model. Okay, so you can think about it. Whenever you deal with a new system, they simulations, you need to write a PDE, right? Okay, so maybe I write it down, PDE. Okay, often of time we need to think about two things. One is a balance principle. Another one is constitutive law. There's an old saying, I think it may be attributed to Trussell, I don't really remember, that we put everything we know into the balance principle, we put everything we don't know into the constitutive law. Okay, so the balance principle is really derived from the Newtonian mechanics, or maybe if you like Hamiltonian or Lagrangian mechanics. They are mechanics derived from material principle. Constitutive law are often based on some assumptions for the thermodynamic consistency. Now, in this case, if we look at the whole course, we have the simpler case, and then we keep adding surgery to deal with different problems. The simplest case is the incompatible two-phase Paul-Messier problem. Is it? The course we have talked about, is it the case? Is it a case? None. The simplest we have discovered, we have talked about. Actually, no. The simplest case we talk about is the Poisson equations, which is assuming that the solid is rigid. Okay? Do you remember that? The balance law putting the Darcy's law, okay? So the simplest case that we first cover is simply the divergence of the velocity, Darcy's velocity equal to 0. Okay, and this is actually the first first balance law we cover, balance of mass. Okay, so if I take account of all the different orthogonal directions for change, and then add it together, there should be no change at all. Okay, so if you look at this cubic, and then assume there's an in and out in all 6 directions. If I add all the in and out directions together, I get nothing, meaning that I did not create mass, I did not destroy mass, okay? And the corresponding Darcy's constitutive law is actually the Darcy's velocity is actually related to k divided by viscosity times gradient p times minus 1. Okay, so this is actually the first case. Now, in the second case that we cover, then we actually relax that assumptions that the material are actually solid phase are now deformable, and then we get the divergence of sigma plus rho g equal to 0, divergence of v plus divergence of v. The Darcy's velocity equal to 0, and because of this term, I need to introduce additional constitutive law, which is actually sigma equals to c double dot epsilon, the linear elasticity, and this is elastic, and I also need to introduce another law, the total stress equal to this minus pi. Okay, this is actually the second. That this is generalizing from the solid part being rigid, and then I add the deformable solid. Okay, so and then what are we doing next? Then what are we doing next is like what we talked about before. We add another phase so that the divergence of sigma plus rho g equal to 0. However, I would consider the deformable material B divergence of V plus rho plus the porosity divided by Kf P dot plus the divergence of V equal to 0. Okay, and for that I need to actually modify this balance of the effective stress principle into the most generalized form. Okay, so the whole course without the numerics from the theoretical part talk about these 3 things. Now, the next thing we need to talk about is the following. What is this and what is this? Okay, you can see the whole train. Okay, if I do dynamics, I also need some new stuff. Okay, But if you actually want to think about what are those new stuff on top of the boundary conditions, is always the new balance law and the new constitutive law. Okay, do you understand that? Okay, the same if I actually want to introduce temperature dependence or chemical potentials or flows on soil. Okay, if you want to generalizing the problem, usually you need to have the right set of assumptions, but you need to actually think about what kind of surgery you need to do for the balance law to make it more generalized. And you also need to think about how do I modify the constitutive law to capture the additional physical phenomena. Okay, it's pretty rare that you can get away by doing one without the other. Okay, you see what I mean? I just want to talk about the big picture because it's towards the end, so I add the new stuff and also do the review. Now, if you think about that, what is the exception where you can get away with one without the other? Do you think of some case? So typically, if you can introduce the new physics, not as a PDE, but as an ODE, you can get away by adding more stuff in the constitutive law. Okay, which we haven't discussed in this course. If you want to learn more about the constitutive law, it will be for the fall semester. If you're already taking it, I think you know what I'm talking about. Okay, it's about more complex material behavior getting captured without considering the spatial effect beyond the first order derivative from the kinematics, which is give us the strength. Go back to what big picture thing is that. So here I have the Tasakis, and here I have the Bills. Now, in order to actually model the free fields one, I need another one. Anyone know the answer, what it is? I need the base shifts, effective stress. Okay, so what is this? That is what we need to talk about. Okay, so now if you consider new material, maybe you can name after one effective stress on your own. Okay, there's already 3 getting named, and there are more than 3. Okay, so if you can think about a more complex problem, the name is still there, available. Okay, think about that. Okay, well, okay, so 11:30. Thank you. So okay, now here we will have 2 balance law. Okay, that we actually need to write. Okay, so the divergence of stress plus rho g equal to 0. This is actually the beauty of it, doesn't change, but I would have 2 balance of mass equations. Yeah, I won't write it out, just too lazy. Okay, and for this solid part, instead of just these 2 equations, I have another water retention curve. Okay, you can write it as the following. You can think about it as the suctions, as the pressure as the functions of suctions and porosity, right? That's one way to think about it. Or you can think about suctions as the functions of the degree of saturation and pressure. Okay, so typically you would use this, but not this. Okay. Now, and then that equations is actually path dependent, but if you don't assume if you're assuming the path dependent is not important, then you can get away from that. And the other change you need to do is that this Dows's law now need to split into 2 Dows's law. V alpha equals to minus K R alpha times K divided by nu alpha gradient of P. Okay, and this is the viscosity. As I said before, the viscosity of the 2 phases doesn't need to be similar. It could be very different. Okay, water and air have very different viscosity. Oil and water have very different viscosity, and hence, even for the material that have the same permeability, you will get a very different hydraulic conductivity. Okay, and in general, air is much more compressible than water. So this is also something that you can consider. Okay, now go back to now we want to talk about one useful relationships we would have is the following. Because the void fractions is related to the volume fractions. Okay. We can also write this. Okay. So one minor the volume fraction of solid is just one minor the porosity. Okay, here. So this term is called porosity. And sometimes we also write it like this because it's actually where the fluid, including the gas and the water, would occupy. Now, a lot of time it's easier to measure the degree of saturations or to use the degree of saturations to give us the concept of how saturated the material is for the void space. So this relationship is often used in the waveform. If I take the time derivative, what we have is this. So alpha actually could be either water or it could be air in this case. Now, if I take the time derivative, the total time derivative of the volume fractions of the liquid phase or the gas phase, we would actually need to take the derivative of in the products rule, and then we will get these two terms. Okay, so far so good. Is that clear? Okay, so let me explain what it is. So if you want to change the one of the liquid phase, either water or air, there's a two mechanism you can do it. You can change how much solid you have, okay? You see what I mean? Making the solid more, or you can actually changing how saturated the material is in a void space. Okay, you can change the volume fractions of the water, but by not changing the solid phase, but just making more saturated. Okay, like you inject the water into a rigid porous media, you increase the degree of saturations. Or you can actually say that I don't have any change in the how saturated it is. I simply have less or more solid that are getting there. So the void space itself is actually getting smaller. Okay, you see what I mean? It's like a stock. You can either make the whole company smaller or bigger, and then you get a change of your money or control, or you can actually just simply have more share, right? Okay. Okay, so now what we actually need to do is to derive the balance of mass first, and then after that going to the balance of linear momentum. Okay. So notice that typically, I just want to get the point to summarize everything. If you deal with porous media problem, my personal advice is to deal with the balance of mass first because it's very intuitive. Do you get what I'm saying? If you think about the mass portion carefully, you can actually see the mathematics connect to the concept very easily because you just need to always imagine there's a ball and there's a multiple specimen there that come in and out, and you can actually derive it. Okay. Before the now, what this lecture about is not about compressibility, it's about having another phase. Okay, so in all these cases, so let me first deal with the balance of the the solid case first. By the way, there is always, when we look at the porous media literature, there is also another two way of dividing the balance of mass. In what we shown here in the course, we always develop the balance of mass for each individual phase, and then we add it together to cancel out the term. But then there's another way, like Jim Rice or John Vedicki, they simply have the balance of fluid mass, and they don't consider the solid. Okay, and that is also okay, because either way, it gives you enough constraint to write the balance law. You should get the same results if you write it correctly. Okay. Okay, so let's go back to this. If I take the time derivative of the solid, I would actually get the term like what I would have for the solid phase, but I would have the pressure change of the time plus the divergence of the velocity term. Okay, so there's this three phase. Okay, now this is actually the new term for the compressible solid. Okay, so what it means is that you can have a porous media that initially look like this, and then it shrink into this, or maybe making it bigger. Okay, you see what I mean? So far so good. Now I will put these two terms in the right hand side, and then I will get this term. Okay, so far so good. Now, why do I get this term? It's because of this. Okay, this is simply the P of the solid phase. Now, if you actually think about it, then this would be related to the minor of the Buck modulus times the divergence of the V. Okay, so why is that? So just look at this diagram, okay? So if the material, if the solid are actually changing the size, and if you want to keep the same, if you want to, okay, let me put another more extreme example so it's easy to see. Let's say that I have an effective medium, and I have these three big particle. Okay, now if I actually look at the effective medium size, maybe something like this. Okay, now if I actually want, if the material are actually expanding, okay, if the solid material is actually expanding, but with a particular volume, then what would happen if I want to keep the same size? Sorry, let me write it more. Let me say it more carefully. If the individual grain are actually shrinking, but I actually want to keep the opposite size, then what I should do? Okay, I basically need to move this thing to this side to actually get these three new particle, and then I get the same volume, right? Okay, so this is actually why we have the minus sign here. Okay, and this is actually why these two things are related to each other. Okay, does that make sense? Okay, the solid skeleton change the size in this. If we keep the same weight volume, then they need to have opposite effect to keep the same size. Okay, so go back to this. So this is actually what we have. And so what we would have for the other phase is actually the following. For all the other phase, then we would actually need to consider the we will actually need to consider these equations and write down what we have previously. Okay. So what I actually need to do is very simple. I just need to substitute this inside these equations, and what I would have is actually the following. So for solid term, the rate of change is actually this term. For the other two terms, what I would have is that I would have the degree of saturation term times this solid volume fraction minus k divided by ks term plus 1 minus the volume fractions of solid times the change of degree of saturations. Okay, so basically this term lead to here. This term is actually just this term substituted by this. Okay, you all see this? Now with that, then with these relationships, then we can actually write the balance of mass for the air, water, and other phase. Now, what I'm actually telling you is basically in the big picture sense, what I'm showing you is the surgery it takes to write a balanced mass, or a balanced principle, okay, to prepare for the numeric simulations. So what we will have is the following. We would actually put back the balance principle there. And then we realizing that in the first term, again, if you remember from the very beginning of the lecture, we only want to keep one type of derivative for convenience, and that is a solid time derivative. So any other derivative would have to converge to the solid perspective, and that comes at a price that it lead to a convection term. Okay, so to measure the difference between the two trajectory, the convection term come up, and that convection term is actually look like this, and we talked about it earlier in the lecture. Okay, now alpha is actually the Darcy's velocity, but then now I have two Darcy's velocity. The Darcy's velocity for the water and the Darcy's velocity for air. Does that make sense? Because the air and water doesn't necessarily to move together. They can move in different directions. Okay, so or they can be followed to each other relatively similar, but then they may not be traveling in the same speed, right? Okay, because you can try to see that if you actually put some oil and water together and you try to have a drum and rotating that, you will find that the oil drop would basically move along with the water, but they do not necessarily always have the same speed. Okay, they don't have the same density. So okay. Now then the second term here, again, because of that time derivative, we actually need to switching that to the solid perspective, and that also gives us another convection term. Okay, you can kind of see mathematically what I mean by the convection term. There's a gradient of P dot the dot product between the gradient of P and then the Darcy's velocity. Okay, that gives us the sense of take account of the change of the P while the liquid is actually moving. What is the what if you actually switch back to the point of the solid, what would be the pressure? And this one would be actually again equals to the absolute solid velocity plus the Darcy's velocity of the phase. Okay, do you know what I'm talking about? Okay, so this one is the absolute velocity. Okay, so and then the Darcy's velocity is actually v of the alpha phase minus the v. So v plus v alpha minus v, so the v cancel out, and then we have the v alpha. So this is actually the absolute velocity of the alpha phase. Okay, and this one is the Darcy's velocity. Okay, sorry, let me spell the Darcy's correctly. Okay, so far so good. Okay, so far so good. Now we need to deal with the rest of the term K alpha. Okay, and we deal with that before. So K alpha is actually the bulk modulus of the fluid phase, okay, either water or air. Okay, that we have. Okay, so we have these candidate equations, and if I go back to these, so what is K alpha? So now let's go back to the previous ideal gas lecture. Okay, so basically if you remember, for ideal gas, PV divided by T are actually constant. Okay, so this is actually for the ideal gas. Okay, most of the things we deal with are not gas, or they may not be ideal gas. So, but what we actually could do is the following. If the temperature that we consider, if the range we consider is actually very limited, okay, then we can actually assume so we can assuming that that the temperature dependent is not there, okay, and that would actually give us the biotropic flow. So it sounds, if you remember from the last lecture, what it means is that there's a unique relationship between the pressure and density. Okay, one pressure gives you one density. If I increase the pressure, I get a different density. Okay, which is not true, because in real life, if you actually change the temperature, you would also change the density, right? If you look at the molecular dynamics simulation, you increase the temperature, those molecules start to move, okay, more violently, and then it won't hold in the same temperature. Okay, but let's make the assumptions to make it easier, because if you deal with the material that doesn't change that much temperature relatively, maybe it doesn't matter. Okay, so in these definitions, where the temperature is taken out of the picture, Ka is simply the rho, so K alpha is simply rho alpha times the partial derivative of alpha with respect to the, partial derivative of the pressure for the alpha phase with respect to the change of the temperature. With respect to the change of the density, intrinsic density in this case. Okay, so which is actually equal to the m of alpha divided by v of alpha. Okay, intrinsic, not the partial. That is very important. Now, if we actually take the time derivative, so what we would have is that, I think I need to use the total derivative. If I actually take the time derivative of this K alpha, there's also another expression, is that, let me consider these alternative definitions. I'll take the time derivative in both sides. Then what I would have is that I would have a Ka times the change of the density over time equals to the density, intrinsic density, times the change of the pressure over time with respect to time. Okay? Does that make sense? Well, I guess it may or may not make sense, but what the consequence you can see here is that PA times VA is actually equals to PA times MA divided by rho A equal to constant. Okay, so kind of like the ideal law thing, but I just simply put T there times the constant, and I'm assuming that the T times constant is also a constant itself. Okay, you see what I mean? Okay, again, if you want to model magma, you probably don't want to assuming that, okay, this is a couple thousand Celsius or something that very hot, very close to phase diagram, very close to the phase transition, this thing doesn't hold. Okay, but if you consider very cold water moving or near the room temperature, is actually not a bad assumption. But always understand or remind yourself the limit of the theory is very important when you want to formulate a new model, because you know exactly where you want to change. Okay. For biomechanics, it's the same. Although I don't think in your biological material you have air bubble. If your air bubble, probably is not a good sign for the human. Definitely. But you can actually assume a biotropic flow because the temperature of human body regulate. Okay, so go back to this. If I actually using these equations, what get the equation? Substitute about this. Summary I can do is that I can actually, let's say I actually assuming that this is actually constant. And so I can take the time derivative of in particular the air. And what I would have is that I would actually have two different terms. This is just from calculus. Okay, you guys know why the rho A is square? Just the rules to deal with the derivative of something divided by something, okay? Now this one is actually equal to 0 because this is constant. So if I take the time, so PVA is actually equal to PAMA divided by rho A. Since this is constant, if you take the time derivative of this whole thing, then the change of the constant is nothing, right? It's 0, okay? So this thing is actually giving us 0. So now the reason I want to do this is that if you do a little bit of algebra, what we get is that rho A, PA, DAM, A, MA, KA, minus PA. Okay, so we write these equations, okay? Now, what is actually interesting is the following. Since I cannot create or destroy mass, I would say this term is equal to 0, okay? Now, and this term, I would assume that because I deal with the free phase, this term is not equal to 0, okay? Not necessarily equal to 0, more accurately. Okay, it could be equal to 0, but it could be also not equal to 0. Okay, so now if this term is also not equal to 0, okay, then what would equal to 0? So the Ka is actually equal to Pa. Isn't it interesting? Yes, that only works for ideal gas. Okay, by the way. Okay, sorry. This only working for when you have PV equal to constant, okay? But keep in mind that PV is not equal to constant in real life, but if you actually consider very small temperature change or material that are outside phase diagram, it will work. If you want a similar explosive, that definitely won't work, okay? Because you have to consider the temperature. Okay, and you may actually also doesn't have a linear relationships that you can describe in terms of one single buck modulus for the volumetric response. Okay. Now this is a big assumptions, but in some case, this is actually what we use. Okay, so now going back to this, go back to the same thing about some mass business. Now I would actually stock modulus, well, relationship there. So what I would have is actually this term. Okay, so it looks pretty complicated, but remember that what we had before. What is this? What we had before in the compressible single phase linear elasticity is that this whole thing become 1, this whole thing become 1 only, right? You see what I mean? Now, with the free phase, we cannot complete it with one equations, but we have all the other extra term. Okay, so this is not complete, but we would also have to consider the change of the degree of saturations, the impact of that, and all the convection term that come along with this. Okay, so the term get way more complicated. Now in general, we would group all those terms here to call it just a mass term m alpha, and then I would actually use some derivations on this term to simplify the deviations. And if I actually do this after some algebra, what I would have is that B times the degree of saturations of the alpha terms times the divergence of V is actually plus the 1 minus rho s, which is actually, theta s, which is give us the porosity times the change of the degree of saturations plus m alpha is actually equals to minus rho alpha divergence of alpha. Now in your implementations, you just need to divide the whole thing by alpha by the volume fractions of the alpha term. Then you have the divergence of V, like what we previous divergence of the Darcy's alpha term equals to B divided by rho B divided by the volume fractions of the alpha term times the degree of saturations, the solid, plus 1 divided by rho s divided by rho alpha, which is actually what? These two terms is simply 1 divided by the degree of saturations of alpha, right? Times the T times the change of the degree of saturations. Okay, or maybe let me do it this way. Okay. So far so good. Okay, this gives us the balance of mass. Now, you will notice that I keep the alpha term there. Why? Because if you think about it, what is the minimum I need to solve? I actually definitely need to still find the displacement of the solid, and I definitely still need the pressure of the water, right? But now, at the very least, I also need the pressure of air, right? Okay, you see what I mean? So instead of one balance of mass, I need two balance of mass so that I have enough constraint. Okay, so that's why I keep the alpha term there, and alpha could be either equals to W or A. Okay, so three set of equations, not three equations, three different type of equations, one balance of linear momentum and two balance of mass. Okay. Now, there's also, let's take a break first, okay? Let's come back at 11:30, and then we'll finish the balance of energy, and from that we will get the balance of linear momentum. And again, we talk about the balance of mass. Now, let's look at the energy. M is actually coming from this whole term that arises from the convections, the term of the Darcy's velocity, and the specific storage of the material. Okay. Okay, or the power, or the change of the internal energy. So the change of the energy is actually related to the conjugate pair of relationships. The first one will make the total stress times the rate of change of the solid, which is actually identical to what we have. The second one which actually related to the term that we have relative on the pressure of the fluid phase that are actually done on the solid part. Okay, in the previous case we only have one. Okay, P alpha, this is not A, P alpha is just one P. Okay, P of the pressure. Okay, and we don't have degree of saturations because in fully saturated case the degree of saturation is equal to 1. Okay, so and in the previous case B also equals to 1 now, but these all assumptions are now generalized. So the solid part are compressible, and hence B is not necessarily equal to 1. And then the degree of saturations is also not necessarily equal to 1 because you need to accommodate the fact that the void space can be occupied by either the water or the air. And hence, we also have two different kinds of pressure. The pressure of alpha that actually represent the pressure of water and the pressure of gas. Okay, now there's also a new term that they come up, which is actually related to the work done of in the porosity in the void space, where the pressure that are actually present in the void space are changing the degree of saturations. Okay, this is a new type of the work done in the void space. Okay, there is a solid, so in the void space there is an air and a water, and then by the relative pressure that they inject into the void space, it would actually lead to the change of the degree of saturations. Okay, more water, more air, less air. And then there's another term that coming from the previous gigantic term from the convections that are related to the M alpha times the P alpha. Then I won't write down the details just for simplicity. So now there's a free pair of the terms, okay? And now if I actually rearranging the term, I would have the total stress plus BPI identity matrix double dot epsilon S dot, okay, which is actually the same as the fully saturated term, the first term, okay? Because if I actually add the two terms together, I simply get back 1, right? Alpha here is only for W and A doesn't include the S term, okay? Okay, this is the first term, the same as the compressible elasticity. Now, then there's the second term that are related, that are unique in this case, but they are actually for the change of the degree of saturations. Now, if I write out the two terms and I only take one of them just for convenience, I will keep the W term because the W term gives us so this term is actually, so the void fractions of the water is actually equal to the degree of saturations of water from your undergraduate course. And this is usually picked to write the balance of linear momentum, to write the constitutive loss simply because it's more intuitive. Okay, so you can pick the other one. Now this term is actually very unique. This is actually called the suction term. And then the last term is actually related to the M alpha, the rest of the term, the work done by the other term. Okay. Now this suction term is relatively important because it's very important for the mechanics problem, for the free-phase poromechanics problem, because it tell you the relationships between how easy the water can remain on the void space. Okay. So what gives you suction? What kind of what kind of machines will give you suctions in your household? Yeah, vacuum. Yeah, okay. Why is a vacuum able to actually? Okay, imagine you have a vacuum that can work for carpet. It can suck water out from it, right? What causing it? So I would have to apply air pressure, right? Okay, so enough so that even the water droplet are actually getting extracted from the carpet, right? Okay, it's the same thing here, okay? It's not the pressure itself that triggered the phase change, is the difference between the two pressure, okay? If they're in equilibrium, you cannot change if they're identical, you cannot change the degree of saturations. Okay, does that make sense? Okay. So what actually happened is the following. We need to look at each of the conjugate. So, and then we have to consider each of the conjugations, conjugate pair separately when we actually try to write the constitutive law. We can call it conjugate relations or conjugate pair because a conjugate relationship always come in pair. The first one is the effective stress, the total stress to the solid. It's the effective stress, sorry. And this is actually governing the solid constitutive response. Okay, so typically what we did is that we say epsilon s double dot c e is actually equals to the effective stress. Okay, for example, but it can be also be nonlinear relationships, a hyperelastic energy functional, plasticity model, etc., etc. Another one that are actually new is these relationships. Is the one minor the volume fractions of water times the suctions S, which is actually the difference between the water and air pressure times and the degree of saturations. Okay, so this is actually called water retentions relationship or water retention curve. Okay, why is it called water retention curve? Because this relationship is actually telling you what kind of suctions I need to keep a certain degree of saturations. Okay? If you work for our company, you need to really know this. This is very important. Okay. So far, so good? Okay. Now, each conjugate pair, if you look at it carefully, each of pair require one constitutive law. Okay? You see what I mean? So in your solid mechanics, you only need one constitutive law, and that would be the mapping from the strength to the stress, okay? Okay, it could be linear, then you write a elasticity tensor. It could be nonlinear, where you actually use more things to describe it. It could be isotropic, so you just need Young's modulus and Poisson ratios. And then we have the water retention behavior. Now, this is actually new. And now we still have the previous one that actually exists, which is actually the Darcy's relationships. The Darcy's law for water and the Darcy's law for air. Okay. Now for three-phase model, we actually need 3 types of constitutive law and 4 constitutive law. Okay, does that make sense? Okay, so you would think that if I add one more physics, I need one more constitutive law, but that's not the case here. I need 4 more, okay, just to introduce one more phase, okay? And this is under the assumption that the air and the gas phase and the water phase cannot have mass exchange. Okay, sometimes you could have, like if you only have water, but it's so hot that it could actually have stream, okay, evaporize, so okay. Then you have to think about the phase transition as well, which is another constitutive law, and you do have a gas phase, which is also water, but now in gas form, okay. Now then, you also need to consider the temperature, okay. So in more general applications, the multi-physics problem will be you need to incorporate even more physics, and then the burden for the numerics is even harder, okay? So the Darcy's law, I will talk about it later, but let me talk about this water retention curve, okay? And I would say the following. Okay, by the way, there is a reading, I think it's from Shell, or maybe from ExxonMobil, I forgot. Or actually from number J, that is called fundamental of wettability, which I will recommend that you take a look. You can just Google it. It's actually there to talk about it, okay. Wettability is a very important topic. It affects from the car manufacturer, the cone that you need, the computer, the iPhone, the computer screen, all the way to oil, petroleum engineering. The fundamental availability is a very important topic, and you're often manipulating it to achieve certain goal for your device, or you need to understand it to actually extract more oil, or actually have a successful CO2 sequestrations or nuclear waste disposal operation. They all require the understanding of wettability. So that's important as the diffusion itself. Okay, so let me actually talk a little bit about this wettability relationship. Basically, what we need to understand is the relationship among 3 physical quality: the porosity, the degree of saturations, and the suctions. Okay, how are the 3 things related? You can imagine that if you have more voids, okay, you can easily contain more water, okay, but you actually also have need a different amount of suctions to actually make the material fully saturate. So again, this is actually suctions. Okay, this is the degree of saturations of water. And the last one is just a porosity. Again, we developed by VT. Okay, from your undergrad. Okay, how does this 3 thing relate? Okay, this is actually something very interesting, in fact. It's related to what we talk about, the regimes, where we form liquid bridge, form liquid patch, all the way to bubble. They have a different amount of they have different mechanism, okay, between the fluid solid interactions, and that actually lead to the following behavior. You will have the suction there that are actually equals to PA minus PW, okay, and what you would actually see is the following. If you're actually trying to make the material dry, okay, that meaning what does that mean is that I'm going to decrease the degree of saturation, right? Okay, so the curve that you would usually see is like this. Maybe I use another. Okay, it's usually like this. Okay, there is a particular name on it. It's called the drain gauge equilibrium curve. Okay, so you will see that at this part, okay, I need to take a lot of effort to reduce the, I need to actually increase the suction a lot to change a very little degree of saturations, okay, as I start to pop in more bubble, okay. And then all the way to here, I enter a zone that are relatively easy, okay. And then at the end, it's also getting very hard, okay. Okay, does that make sense to you? Okay, when you want to push the air bubble, okay, you can argue that when you want to get the air bubble in the fully saturated material is hard. Okay, once you have enough air bubble, the air bubble coalescence, you enter a phase where you can easily add more air to it, okay, until the way that you start to actually dry, okay, and then you, not the side, not you, but the boss media start to get dry, and then we have the liquid bridge that are sticky on the solid phase, and so it becomes harder again to get the last drop of the water completely dry, right? Okay, imagine that you have a towel and you try to squeeze the water out. Okay, it won't be completely dry, right? Okay, if it's completely dry, that would be good. Then we don't have to the laundry will be much easier to do, right? Okay, so it's actually related to the regimes that you're in on the and how does the weatherability play the role. Now, the interesting thing is that if you're wetting it, not drying it, you have a different path that look like this. Okay, usually the end path get pretty close, and this is called the imbibitions equilibrium. Curve. Okay, simply call it the wetting. Okay, now the most important thing to see is the following. Okay, this part in this whole curve doesn't start at the 0 degree of saturations. There's a residual there. Okay, so what it means is that you can increase the suctions, but at some point there's a droplet of water that are isolated and you cannot make it completely dry. Okay, the only way you can actually using the suction to get out the last portions of the water is through maybe phase change. Okay, you just increase the temperature, you put the wet coats after you put it in the dry to the sun, okay, and then get all the water, actually get the rest of the water out or whatever in that analog. Okay, this is actually the portions of the water that are not possible to withdraw from suctions alone. Okay. Okay, in an analog, it's like if you have a carpet and you have the water vacuum, actually you can suck out the water, but it won't be completely dry. Okay, it will be drier than before. Okay, and if you look at the microscopic thing, you see you still have droplet here or there, but they should be in droplet form. Okay, they shouldn't be in the other form or have patch or have bubble or locally fully saturated with a very large portions. Okay, so now this is actually getting hard because this is path dependent. Okay, now actually let me ask you one question. What if I wetting it and then suddenly I dried it? What would happen? This is also what if I actually, or maybe I dried it. Let's say I go all the way to here and then I suddenly wetting it, so what will happen? What do you think will happen? I won't go directly here, right? I won't have a jump. Okay, so what would happen? Just make a guess, okay? I can tell you it won't go vertical. Okay, does that make sense? Okay. It will go somewhere like this. Okay, we have a little bit, and it depends on the material. Some material will have a less of these portions, but it will go down like this. Okay, does that make sense? And eventually they may fall into the same path. Some of them may be something like this. Okay, it's also possible. So you can think about this. This is like a 1D passivity problem, right? Okay. Do you know why? Because this is one variable, this is another variable, and then they're path dependent. Okay, so the suctions relationships are actually, in other words, at least path dependent. Okay, in particular, we actually need to consider the multiple case where for some material the gap between the two are actually really large, but in other case, then we would actually not modeling those details. Okay, just for simplicity. Now, this also comes from another numerical difficulty. Notice that in between here, okay, you would actually have the degree of saturation not equal to 0. Okay, you see what I mean? Okay, so this is actually because you're assuming that some part of the water are actually not able to clean up by simply suctions. If you set everything equal to 0 in your initial setup, let's say you want to simulate a wet material, and then you set it to 0, and then this curve is actually going to infinite, which has actually happened a lot of time, because a lot of time these relationship are modeled in the log scale. Then what would happen is that you would actually have not a number calculations, and that is actually due to the fact that your model is not initialized properly. If you want to model the unsaturated one, make sure that the curve is actually start somewhere here, but not actually here. Okay, this is a common mistake people make. You start from here. Okay, it won't work. Okay, or actually going other way is the infinite point. It also won't work. Okay, make sure you set it up the initial state that are actually at equilibrium. Okay, that will require some calculations. Now you can look at these. I think the application is after all the simplest one, and then still the most popular one that are used is to collapse the drying curve and the wetting curve and result in one single curve. Okay, so the original curve looks like this. If I don't care about wetting and drying, I want to just get a rough idea. So what is the right way to doing it? I'll just take the middle. Okay, this is actually, I think I forget how many citations, maybe a couple, 4,000 or something. That's the whole idea of these. When Gentin, I think I forget where is the original country. I think it's from Brazil. Anyway, I could be wrong, and then unfortunately. Okay, so if you only care about the yellow curve, okay, that means you collapse the wetting path and the drying path into one path. You lost the accuracy, but you significantly simplify the model. And that model actually have a specific form where the degree of saturation of water is actually assumed to be related to S1 plus S2 minus S1 times 1 plus S divided by SA times N minus M. Okay, so let me explain what is S1. S1 is actually the suctions at which you're increasing and increase further, it won't change the degree of saturations, okay? And S2 is actually the endpoint where the degree of saturation is the highest. And oftentimes you set it to 100, but sometimes not. Okay? There's also another possibility that no matter how much, how little suction you have, you will still have some residual bubble that you cannot get out. Okay? Or maybe oil. Okay? This, by the way, this is actually working for any retentions. Okay? So not just for the air to water, but water to solid, water to oil, not solid, or even ice to water, okay? Now ice is solid, but why would ice and water would also use the retention curve? It doesn't make any sense, right? Why is that? I can explain it maybe in another lecture, but the long story short is the following. You have an ice crystal, okay? Let me use the blue color to write the crystal. And I actually underneath it there's a solid. Okay, what happened to the ice crystal is that it's not going to directly touching the solid phase, okay? This is called the pre-melting theory. And the reason is that the surface energy difference will allow the water thin film to form in the ice between the ice crystal. Okay, so the ice crystal is not touching any solid, and hence it can transport in the void space. Okay, and this is actually the assumptions of the water retention curve. Of course, if the whole thing become completely saturated with ice, then it doesn't make sense because the ice will be so big that it cannot transport anyway, right? And then there will be no water thin film when it completely frozen. Okay, but before it completely frozen, the water is supposed to be surrounding the soil. Okay, so the water thin film surrounding the solid and the ice, so that the ice doesn't form when attached to the solid. Okay, this is assumptions. There are some special case. For example, if you have a clay, it have a hydration, so it may absorb the water, or you can actually have other things like ice lens. Now, but going back to these equations, so S1 and S2, as well as N and M, are actually a numerical parameter. Okay, so, and what is SA? Okay, so A stands for the atmosphere pressure. Okay, so what actually you're calculating is the A atmosphere pressure minus the pressure of water. Okay, so this one. Okay, so because you need a reference point and the atmosphere pressure is the reference point. Okay. And then you can get this curve. Sometimes people like to take a log on these equations. Now, notice, let me say that again. N, M, S1, S2 are material parameter. Just like Young's modulus and Poisson ratio are parameter. Okay, and they're the material parameter of what? Is it the fluid? Is it the solid or is it the air? This is very important questions, okay? Is it the solid? How many of you think it's not solid? I saw George. I thought. Okay. How many of you think is the property of the water? How many of you think is the property of air? I saw it. Okay, so let me tell you the answer. The answer is all of them. Okay, so it's important because it's a three-phase interaction. It's a three-phase interaction that gives you the N, M, S1, and S2. So to give you an example, if I have the same water, but on a plastic domain and in a clay domain, I have a different retention curve. Okay, same water and same air. On the other hand, if I have the same solid, but I change the air to oil, I will have a completely water retention curve. Okay, it's the surface energy difference between all three of them actually give us the retention curve. Okay, So brine water and clean water, of course, would already make some difference. And here we don't talk about the possibility of the solution getting crystallized. Okay. Okay, so this is actually more complicated, but make sure that if you want to model something else, then you need a different retention curve, and you need to experiment to model the retention curve. In principle, the retention curve also depends on temperature. Okay? The retention curve is not fixed, it also depends on temperature. But on the other hand, the viscosity is also depends on temperature. Higher temperature gives us less viscosity, and hence you also have a different Darcy's flow behavior, and that actually everything is actually coupled together. Okay, so there's also another important concept that generalized from the Darcy's law. This is not the linear relationships. Okay, so for unsaturated porous media, there is no analytical solutions for any of the governing equations. Okay, maybe we can use symbolic regression to find one. Okay, but right now, all the verification problems, they are not coming from analytical solutions. Okay, and also, as you can see, is as I increase the physics law, I actually need to introduce more ad hoc assumptions. Okay, previously I just need to find the Young's modulus and Poisson ratio and permeability, and that's it. Okay, now I actually need to come up with way more. This is a 1D curve, okay, but in that 1D curve, I need to actually have 1, 2, 3, 4 parameter that actually need to calibrate from experiment. And N and M are just curve fitting parameter. You can argue that S1 and S2 have physical meaning. N and M are just a curve fitting parameter. That being said, this is important to know these equations because this is highly used in applications and highly used not only for predicting code in a finite element code, but also for analytical solution, for analysis. Okay. You need to see how easy to extract the oil. You need to know this. This is crucial. Okay, the UP formulation doesn't give you how much oil you can extract. It's from this. With the availability, we understand the relative hydraulic pressure or you need to do in the production well in order to extract the oil. Okay, of course, if you model it better, you can actually get a more precise predictions. And again, this is not only for porous media. I have a lot of application for even for battery or for chemical engineering. There's a lot of work related to this. Go back to discussion. Okay, so you remember what is Darcy's law? I have this derived from Harry Darcy. High pressure, low pressure, water moving this way in a porous media, and I can actually calculate the pressure difference, and I would actually get a velocity. Okay, the higher the pressure difference, the faster the water flow through. Now imagine that's the two different phases. Okay, so I need to actually, for the fully saturated case, the relative velocity is actually related to the permeability divided by the viscosity times the gradient of P. Okay, this is actually a given. Now, what happened to when I actually want to have two different phases? Okay. Now, the simplest case is assuming that V is actually the Darcy's velocity of this is actually related to the permeability divided by the viscosity of alpha times gradient P. Is it correct? It's not correct. Okay, so K itself in general it depends on the degree of saturations. Okay, obviously and sometimes we call it K alpha. So K alpha, KR. KR is actually the relative permeability. It has no dimensionless, and it is actually the degree of saturation. Is the functions of the degree of saturations of alpha. Okay, so let me put the name there. This is the relative permeability. Now you can say that, and one important property of this term is that if the degree of saturation is actually equal to 1, then Kr also equal to 1. Okay, is the one that usually we would have, so that we can recover the fully saturated behavior when the permeability is actually when the void space is only saturated with one single phase. Okay, so this is actually again dimensionless. Just a scaling factor if you think about it. Just a term, okay? You see what I mean? So when you work on the porous media, three-phase porous media, you need to think about that. If I actually make the degree of saturation to 100%, can I get the UP formulations? And when the degree of saturation go to 0, do I also get the UP simulations, but the air effect would actually be very limited to the solid mechanics response? Okay, why is it very limited? So air is compressible, okay, and air is actually also a very high Dawson's law. So it basically doesn't, unlike the water, unless it's completely undrained, then you will actually get the incompressibility. The permeability is very high, meaning that you cannot have that much exceeds air pressure in most cases. So if the exceeds pore pressure equal to 0, then basically the total stress is equal to the effective stress, okay, or more or less equal to each other. And so the air effect is actually relatively small, okay, unless in the undrained conditions, which lead to a very unstable system. But in both cases, all the other case, then you need to think about the retention relationships that actually govern the saturations, and in that saturations, in a particular saturation, how easy the individual liquid phase flow within the void space. Okay, you see what I mean? Okay, and solving the problem is much harder if you actually try to build the boundary value problem, because, okay, so far so good. Any question about the theory of three-phase porous media? Okay, how many of you want to have final project for the three-phase material? No one. Okay. It would be good to always challenge yourself if you like. Okay. So, but remember that there's no linear counterpart on that. Okay. Unless you assume a linear retention curve, which in that case won't be very practical. Okay. Now, I want to talk about the simplest finite element formulation possible for that retention problem. And again, modeling this is also more difficult because you have two different hydraulic conductivity. And what it implies is that your matrix system now becomes a 3 by 3 matrix. Okay, sorry, not 3 by 3 matrix. It's a 3 block by 3 block matrix. Okay, you're a block matrix system and you have 9 different blocks. Okay. And you would expect that in general, the conditional number of the 3-phase is also much higher than the 2-phase. Okay, no matter what you did. Okay, because the conductivity of the air and water, they are very different. So no matter how you're modeling it, you would actually need to live with a very high conditional number just because fundamentally they're different. Okay, and they are fully coupled. And then you have the solid system that are actually also have its own set of eigenvalues. And they are also coupled. So Okay, so but let's talk about on the upside what we can do with that is that on the other hand, in general, you can model this again with a Taylor hook element or with a stabilized Fowler element. You have one set of equations, the divergence of the total stress times the body force equal to 0. A 0 is not a scalar, a vector here. And I have the degree of, and I have the balance term that depends on the degree of saturations plus the change of the void fractions term plus the direction term of the Darcy's velocity of the solid term. Sorry, of the relative velocity term times the specific storage term plus the term that are actually lead by the convections. Okay, all these terms together, and then that will give me equation 2 for the air and equation 3 for the water. But then the form of the equation 2 and 3 are actually identical. Okay, so far so good. This is actually the strong form statement after you add the boundary conditions. Here. Okay, so that you swap the degree of saturation as an unknown to the pressure, so to the pressure dot. Okay, so this will be rewritten as a PA dot minus PW dot. Okay, so then you have the UP formations. Now, if you are trying to extract something very valuable, there's also another trick. You would not, sometimes you will not write UPP formulation, you will write UPS R's equations. Okay, you will try to discretize the degree of saturations. Now this may make the problem even harder, but it has one very important benefit. What is that benefit? Your degree of saturation is at the NOx, meaning that I have the degree of saturation field. Okay, and sometimes you care about the degree of saturation field because that tells you how much water or oil are actually there. Okay, so sometimes people try to do that. Now, but what is the drawback of writing the degree of saturation field as an unknown? What is the difficulty for that? There's a big difficulty for that in the sense that P could be any real number. Okay, in principle, it could be minus infinite to positive infinite, not reaching that to infinite, but very close to that is actually numerically legit. Can you have negative degree of saturations? You cannot, okay? It can, so it's actually bounded as a real, positive real number or non-negative real number, okay? So what is the problem with that? Is that there's no problem with that until you actually write your governing law with the gradient, divergence, or stuff that can give you unphysical negative degree of saturations, okay? Your constraint itself, if you don't write it properly, could give you the negative degree of saturations or numerical insolubility, and also that usually also lead to different condition number. So, in principle, it seems complicated, but I would say that if you sort out the detail, it's not that hard to put a UPAPW system there, okay, if you don't add the dynamics. Okay, if you add the dynamic, I agree that it's actually too hard. You simply need 2000's law, one retention curve, and you need a Newton-Raphson algorithm to solve the nonlinear elasticity. Okay, so, but this is actually certainly doable. Okay, and of course, you can argue that the UPAPW formulation is much powerful than the fully saturated counterpart. but you actually need to measure way more in order to achieving your need for computing the model. Okay, does that make sense? So in principle, the element you can use are actually still very rich, but one thing that would work is a terahook element that actually have 9 nodes. If you use a quad element for displacement, so give you a quadratic polynomials, and and you can use the 4-point to form a linear basis for P, and also linear also for PA. Okay, so let me put the color there. So the green one is a displacement nodal solutions for solid. The yellow circle is actually the pressure of the water. The air is actually the pressure of the air. Oh, by the way, I forget to name one more trick people often use. Sometimes we still solving the 3-phase problem with only UP formulations, and what is how to do it? Can you guys make a guess? How do I do it? That will make it much simpler, okay? I just have one scalar and one vector, okay? But I have to make another assumptions for the sake of that simplicity. I can kill off the degree of freedom of PA, okay? And that would be very simple. In a special case, I will assume that PA is always equal to P atmosphere. Okay? Then it's already known. Okay? Now, is it accurate? It's not that accurate. Okay? You may underestimate, overestimate the settlement, the leaf, or whatever, but you can use much better than the UP formulation assuming fluid is accurate. Okay? So, you see what I mean? When you're modeling, you always have tons of choice, okay? The more you're unable to compromise, the more complicated the model it is, and sometimes that compromise is not a good idea. Sometimes you're just doing it to get the analysis finished quicker, okay? And you'll be surprised. In the geotechnical engineering practice, we make a lot of compromise, and we add a very big factor, 10, 20, just to cover that simplicity, while we have all the tools to make it more accurate, okay? But sometimes you can also argue that simple models are actually more robust, so I mean, I don't want to get into that philosophical debate on that. Okay, so this is the final element. Now with the final elements, what we actually need to do is to list all the facts. Now I have the balance law, the rest is the constitutive law. So I will put the constitutive law into two. One is actually really the material law. Another one is the effective stress principle. Okay, so the effective stress principle is the following. We would actually write the total stress is actually equal to the effective stress minus B, which is the Beer's coefficient, times the degree of saturation of PW, plus 1 minus the degree of saturation of PA times the identity tensor. Okay, so this is one form of the effective stress coming from the unsaturated equations you can think about and sometimes we call it the Bishop's effective stress principle, which is a generalization of the Beal's effective stress principle, and Beal's effective stress principle is a generalization of the Tasaki's effective stress principle, which you learn from the undergraduate soil mechanics. But in terms of the time, okay, each generalizations probably take 30 to 30 years each apart, something like that, okay, give or take. Okay, so the Tasaki equation 90 is around World War One, 1914-17-ish. I forgot about the exact time, sorry. And then the Beal's coefficients 1961, and then the Beal's effective stress 1960 something, and then the Bishop's 1971, if I remember correctly. So you can see that there's a generalization. So you start to understand the specific case and you generalize. Okay. Now this is one part of it. Another part is the material law, which seems very ambiguous, but I will challenge you to try to organize your thought into different set of constitutive law. The first set that is actually the effective stress relationships that give you the strain or strain history and give you the Cauchy effective stress. Okay, this is the first one that actually universal for anything with solid. You always need that, okay, because you need the stress. From the stress, you can actually calculate the direction of stress, which give you the density of the force, and then you actually do a volume integration, you get back the force, okay? Now, the second one is the retention behavior, which is actually like what I say, writing it as the degree of saturation of the suctions, and sometimes also the porosity. And the porosity is actually related to the displacement itself. Okay, for simplicity, I'll just put the suction there. Okay, can you all see the relationship between the porosity and the solid deformations of the solid? Okay, so there are very simple relationships, okay? If I actually have a void ratio, okay, in large deformations, the initial void ratios, okay, times the Jacobian, which is the deformation gradient, the determinant of the deformation gradient equals to the current deformations for incompressible flow. For incompressible solid, for small deformations, is roughly equals to 1 plus the diagonal term of the strain tensor times the initial porosity equal to the current porosity. Okay, assuming that Ks going to infinite and Kf also going to infinite. Okay. Anyway, so go back to this. Now this is the first equations, solid constituted law, and the second one is retentions, which will tell you the relative relationship between the water and the air in the porous space. And then the third one is actually the fluid transport. Okay, which primarily depends on the pressure gradient. Okay, let me put a gradient there. Okay, for constitutive law purpose, to actually govern a more generalizing this, I will put the S there. It also depends on the suction itself. And this one would also depends on the divergence of V itself, or the epsilon S, if you will. But at the minimum, I will take out the yellow part, and this would be the least amount of the constitutive law you need to consider. 3 of them, okay? So the solid and the density law are very similar. It governs how the things are moved for whatever force or pressure you can put it there, okay? And then the retention curve, on the other hand, is something new. It's telling you the relatively how easy to squeeze one liquid over the other, given a certain pressure difference, okay? So far so good? Okay, now we need to derive the width form. If you actually remember how do we divide the width form? How do we divide the width form? In a way, residual argument. I think there's one necessary condition is that if you want to write out the width form, your hand need to have enough rest because you need to write out lots of terms for the next 10 minutes. So I would actually not write out all the individual terms, but you can actually find a paper, or I can give you the material that for you to read. Now, the important thing about this is that these all need to put into the formulation. So eventually, all the mathematical equations can only be a functions of displacement, air pressure, and water pressure. Okay, does that make sense? Okay, and one thing that are also important is the following. It's actually a little bit of important reminder. You do actually need to the following trick secondary dependent here. So I'm assuming that in reality that also depends on the volume fraction or volume deformations. That also depends on the suction. And then so the whole thing are actually fully coupled to each other. Balance law. I'll show you to make the modeling a little bit easier for the balance of mass. Okay, so I have that two phase. Okay, the degree of saturation term and the volume fraction term. Okay, and then I'm going to, for simplicity, a lot of time we're going to assume it's more or less constant. Okay, and that take out what we have. The second, I was actually, for simplicity, I just assume it's constant. Okay, for a given point. Okay, assuming what I mean is that I'm assuming that more accurately, I will assuming that the change of this is small, and the change of this is also relatively small. Now, if you use a code that have automatic differentiations, you don't actually need to assume it's small because you don't actually need to compute the derivative yourself, but then the system would be highly nonlinear and will be harder to solve. Okay, you see what I mean? Now, if you assume this is actually small, then what we actually could do is that we would actually simplify. We simplify some term there, and then we can actually write the Darcy's velocity, just like before, as a functions of the relative velocity divided by the volume fractions of the solid, just like previously how we relate the Darcy's velocity with the relative velocity. Now, one thing that are actually also specific for free fields, maybe I add another phase there. In the which is actually specific for three-phase system is that in the void space, there's only two phases, okay? The solid and the liquid. So we have that interesting behavior is that the change of the water phase, degree of saturation of water is equal to this degree of saturations. But the change of the air phase is actually equal to the negative of the change of the water phase. You see what I mean? One's gain is one's loss. Does that make sense? Oh, I think, do we still have 5 minutes? 6 minutes? Okay. Now, also another relationship that are actually important is that if you take the derivative of S, the relative the degree of saturations, you would get the tangents of that with respect to the suctions times the rate of change of the suctions which is actually just according to the chain rule. Okay, so what is this? This is the water retention curve slope. Okay, so this is actually this curve where you have a suction here and you have the degree of saturation of water, this curve. Okay, this slope at any point is actually the degree of saturation change with respect to the suction. Okay, so you need this SR dot term